just as it goes through time, the spatial dimension is warped, so it looks like it's moving. Okay, so let's go back to this. Let's say that this is Earth, okay, where this guy is, and this guy is in free fall. He's the ball, okay? The balls and the Earth are both moving through time, right? On this geodesic. They can't move in parallel paths like in outer space because space-time is curved. So they end up, they're standing still. You know, their spatial coordinates are staying the same. But as they move through time, they're accelerated toward each other. But it's not by some magical force, okay? They're just traveling through time. It's just that time is now has the spatial coordinates warped. That's all, okay? There's no magic. There's no force. Okay, so I proved beyond a shadow of a doubt that objects do not fall to the ground, okay? They just stand still. As they move through time, space-time itself moves. They actually keep the same coordinates, spatial coordinates. But keep in mind, that's only to the person that is falling with the ball, meaning they're in the same inertial frame of reference. Okay, not to someone on Earth. To someone on Earth, it appears like the ball's falling. Okay, but they're in a different frame of reference. Okay, so I'm not saying to everybody in the universe. I'm saying to anyone in the same frame of reference as the ball falling. Says that, you know, in their frame of reference, the ground is actually accelerating towards them. They are not being accelerated by anything or move, you know, just floating there. Now let's prove that the ground accelerates upwards. Okay, now we already proved objects don't follow the ground. Now we're going to talk about two-dimensional, because four-dimensional pictures are hard to draw. Here's the planet, say. Here's north and south. We're just doing two-dimensional. Now remember, if there was something above the Earth, right? Remember, as it traveled through time, it would form a geodesic, and space-time would be warped, and it would stay in the same spatial coordinates, but those spatial coordinates every second that it travels through time is being accelerated towards the Earth. And it would appear like it would fall. Well, think about it. This isn't actually going to the Earth. The geodesic goes to the center of the Earth. Now think about the north and the south poles. They're both having geodesics, right? You're going to have a geodesic here with this middle of the Earth and north. You're going to have a geodesic here for the south, right? Trying to go, south is trying to go in and north is trying to go. They're both trying to go to the center. But look at the geodesic that's overall made. That means the Earth, this point right here is the same spatial coordinates as this point. And this point here is the same spatial coordinates as this point in time. Okay, as Earth travels through time. These two spatial coordinates are going to converge and be the same point. Okay? Why doesn't that happen though? Okay? Why isn't the Earth crushed? And remember, this is an acceleration between a geodesic, parallel geodesic lines form an acceleration between the top and the bottom if they travel with the same constant speed. And they do through time. They travel relative to each other. They're basically standing still in time. So they're being accelerated at 9.8 meters per second squared. The north to the, being crushed at 9.8 seconds, accelerated toward each other. That is happening. That's a fact, okay? Now, why doesn't the Earth get crushed since it has such a big area or volume here, and down here it has such a low zero volume or area here? This is why. Something can only be crushed so much, and then you have electromagnetic forces take over, because you can only have, protons touching each other so much and electrons before you have an electromagnetic force that pushes outward on everything on the Earth. The Earth is being crushed and crushed, and then it gets to a point, and the crushing is it's an acceleration. Remember, an acceleration. It's acceleratedly being crushed. Okay. Once it hits that point where the electromagnetic forces are pushing upwards and opposite of, outwards, the opposite of what the space-time is trying to do to the planet. And it does that electromagnetic force is an accelerating force of 9.8 meters per second squared. Did you notice how it's 9.8 meters per second squared? That's exactly what the acceleration of Earth is, of our gravity. So you can see the Earth actually accelerates upward and outward, right? And it's just doing it at the same exact rate that the planet is being crushed by the limited space-time volume or area because of the geodesics that it forms. And let me ask you this. When you sit in your chair and you're watching the video, do you feel weightless like you would in outer space moving at constant velocity? Like you were in an inertial frame? Do you feel weightless like you're in free fall? When you're in free fall, you feel weightless. Those are inertial frames, okay? But when you sit there in your chair and you're just sitting there, do you feel like you're weightless? Or do you feel like you're being accelerated upwards? Something's pushing you up, and that's why you feel, imagine if you were in a spaceship. You're accelerated at 9.8 meters per second squared. Or in a car, you're being pushed backwards. You can feel that. You feel you're being pushed backwards because you're going forward. You're being accelerated forward. It's the same on Earth. It feels like you're being accelerated upwards, and that's why you don't feel weightless. That's why you feel like you're attached to the ground. You're stuck there because you're just being accelerated. And also, what does an accelerometer say? If you drop an accelerometer while it's in free fall, it will say that it is not moving. It is not being accelerated. And when you lay an accelerometer down on the planet Earth or hold it in your hand while you're on Earth, it says that it's accelerating at 9.8 meters per second. That's what an accelerometer says. So, and the thing is too, you got to remember, all truths are valid. Maybe only in their own frame of reference, but they are valid in some frame of reference. Okay, maybe not yours, but they are always valid in their own frame of reference. And another thing I wanted to remind you is that you don't need to change your spatial coordinates to be accelerating when you're in a curved space-time. Only in a flat space-time do you need to change your spatial coordinates, okay? Curved space-time is different rules, okay? And you actually can be accelerating without, on Earth, be accelerating upwards and outwards without your spatial coordinates actually being moved, all right? So remember that. And if you need proof, there's the equations. This is the equations for curved space-time. This is the equation for flat space-time. You can see they're exactly the same except for this minus crap right here. You don't need it for this. This is your spatial coordinates. This is your acceleration. You can see in flat space-time, like when you're in outer space, your acceleration depends on this here, on your spatial coordinates, okay? In curved space-time, you actually need to be accelerating just to stand still, okay? This would be your space-time curvature, right? Your speed. You would need this to be, you would need this to cancel out your acceleration. These formulas prove that you actually have to be accelerating in order to stand still in curved spacetime. And you're in curved spacetime when you're on Earth. So you need to be accelerating just to stand still. Okay, so I reviewed the videos I just made, and I wanted to make a couple clarifications. A geodesic is a straight line that is in curved space, whether it's curved space-time or on a globe or on a basketball. It's a straight line in curved space. Parallel geodesic is two parallel lines that are straight, but since they are in curved space, they eventually intersect. Like these two lines are parallel, but since they're in curved space-time, they will eventually intersect. Also, I wanted to mention that not only you can see the space, that's these curved lines, you can see how bad mass will distort or curve space-time. But look at these. These are the timelines. Remember, they used to be straight up and down, and now even they are curved or out, just warped slightly, not as much as this. But even that is curved, okay? So it's not just space curvature that causes things to fall or space-time to move. It's this curvature of time, too. It's just not as pronounced as the space one is. Also, I wanted to mention time is a spatial dimension, just like any other spatial dimension. That's why we have time dilation, because it's a spatial dimension. And also, this is why two bodies or two balls that weigh differently, why they fall or accelerate downward at the same rate. Disregarding air resistance, this is on the moon. Why does this, they get dropped at the same time? This weighs a pound, this weighs 1,000,000 pounds. Why do they hit the ground at the same time? Because they are not falling. The ground is accelerating up at 9.8 meters per second, so it's going to hit both balls at the same time. Since it's, this ground is attached to this ground, they're both moving at 9.8 meters per second squared in acceleration, and so obviously the ground is going to accelerate up and hit both of these balls at the same time. That's why that happens. And the last thing I wanted to say is Earth is accelerating upwards, okay? Not relative to you if you're standing on Earth, but relative to space-time itself. See, here's space-time, but as the planet moves through the Earth, right, the Earth stays this big. Like, say we're at this point right here. The North Pole is still here and the South Pole is still here. But remember, spatial coordinates-wise, the North Pole used to be at this point right here, which is the same as this point. And the South Pole that is still down here used to be at these coordinates and should still be, this is the same coordinates in space. But they're not there. Why? Because the Earth accelerates outward at the same rate that this is accelerating inward so that it stays the same size. So if you accelerate at the same rate as the Earth accelerates upward, you know what I mean? You're not going to feel it as much or think about it as much because you've been like that since birth. It's been like that since birth. You don't even realize that you're being accelerated. But you are relative to space itself, because you can see this space is here, and yet the North Pole would still be up here. So it moved. It moved from this spatial coordinates to this spatial coordinates. From this spatial coordinates to this spatial coordinates. From this spatial coordinates to this spatial coordinates. From this spatial coordinates to this, and so on. It moved because it stays on this path and not this path. So it does accelerate up and outwards, just not relative to you. Okay, relative to space-time itself, it does though.